talk to you. And Giacomo, it's all yours.
Thank you, Raphael. Thank you, everybody else who worked to put together this workshop. And thank you for allowing me and Jerome to contribute to it while being remote. And we will do the best we can to give you as much information to get you started with the software and the methods that it implements. And if you have any questions other than the chat, we will always be reachable online. So I'm going to start by giving some overview of what the software Colvars is about, and also turn over to Jerome later on. The most important concepts, because they're so important, we're going to talk about both of us. So the first, a very brief introduction. What is this software? It's a library, pretty much. It's a software library written in C++ that is specifically designed to implement the kind of methods that, at least the geometric methods that Crescipo has given you a very nice overview about. We call it also a module because it's not a library that we ask the users to download themselves and to patch an MD code to use it. Everything okay there, Rafael?
Yeah, everything's okay. You're just trying to put your picture in the corner.
Oh, okay. Thanks. So it's a module, and because it's not something that you have to be downloading and building and linking simply to MD. If you download MD and build yourself, or if you download a version of MD that was built already for you, Colvars is right there, ready to use. And we have a repository where we develop this code, and we have a reference paper which we published about 10 years ago. There's been numerous papers afterwards for new implementations, and we kind of ask that you acknowledge those as well. And this is the timeline of the development of this code, starting off as something to use in a side project, like many people did. We patch an MD code, we add some custom forces. Soon enough, especially thanks to the collaboration between me and Jerome, when we were both postdocs in my clients group, we decided to make it into something that is good enough, hopefully good enough, to be distributed with the MD engines like NAMD. And that's the relationship we started 16 years ago with the first version of NAMD that was 2.7 that contained Colvars. And the Colvars has since been packaged with other codes, LAMPs, VMD. It's not an MD engine, but it's also very useful, and you're using it in this workshop. Special mention to the dashboard, which is a GUI based on MD, based on VMD, sorry, which is useful to set up and analyze the simulations with Colvars. Jerome will talk about that. And lastly, more recently, TinkerHP and GROMAX also contain Colvars in their main distribution. The theory behind the methods has been already laid out by Chris very thoroughly. And I like particularly whenever I see his lecture, the family tree or like the org chart of all these methods are about, which is reflected in how the code implementation in Colvars is. So the code that Colvars provides has the simple harmonic restraints that you can keep fixed and change them in discrete steps or move them in a gradual manner to do steered MD. We also have, and of course, Chris had mentioned about, I talked about this plenty, the adaptive biasing force method, has a multiple variants, all of which are supported by Colvars and NAMD. And metadynamics also, he mentioned, the classic method plus some of the variants, not all of them. I encourage you to check out Plume if you want all the possible versions of metadynamics. We just include the most popular ones, or at least the ones that we consider most useful for our own projects. There's a glaring omission here, the metadynamics ABF mixed hybrid method that Chris talked about. This is not a specific implementation. This is simply using the same code and turning on both features. The hard work of developing the idea and testing that it works, it was done by Chris and his collaborators, but it's a zero effort implementation in a sense because the library already offers the ability to combine features if it makes sense to do so. This is something that hopefully some of you would like to try. There's also been, other than enhanced sampling methods that are designed to reproduce a PMF, there's other methods that are used to enforce constraints or restraints to conform with experimental data. That has been done in a variety of ways, mostly following other restraints on the histogram or linear restraints following the maximum entropy approach. And it's a library that is primarily for adding restraints and biasing forces, but it can also be used for analysis, and including some that can be done on the fly without having to output very large trajectory files. And all of these sampling schemes or algorithms can be applied to a whole bunch of different collective variable types. This is the full list of what's available with NAM3, and it includes, without going into detail about each of them, some of them were already mentioned by Chris just a few minutes ago. I just wanted to highlight there are some particular features here that are unique to NAMD and VMD that Colvars has support of in its own core shell library code, but relies on functionality that is only present right now for NAMD and VMD. And I will start off with an example. We learn about the functionality and capability of code and methods by making examples concretely. So a lot of my projects and the people that I collaborate most closely with are focused on membrane proteins. And there's been, especially in the past 15 years, like an explosion in the number of structures available, first with cryo-EM, and then with empirical methods like AlphaFold. And all of these methods are really good at giving us fairly accurate structures for these membrane proteins that just a few years ago, when this crystallography structure or the observable solved, it was actually hard to get that many structures by crystallography or like NMR for membrane proteins. One thing that these methods, these structural biology methods give is, of course, the detailed atomic structure of the protein, some limited insight about the mechanism of conformational changes, but they tell us next to nothing or almost nothing about how these proteins interact with the membrane, particularly how a certain membrane protein is embedded in the membrane, what position and what orientation. This is done typically by empirical methods that are based on physics, but are not based on the simulation of actual physical forces. So they're not based on molecular dynamics. But so this is something that you do for the OPM database, which is based on the PPM empirical functional. The Encompass database is a new database developed by Lucy Forrest Lambert and H, which also includes the catalog of symmetries in the protein structures. So if we think about how the protein can be oriented in the membrane, there's mostly two relevant rotations that the protein can have. Once you place it in the membrane, according to whatever initial orientation seems reasonable to you, because it comes from a model or it comes hopefully from experimental information, we know that the protein will like to spin around. If the membrane is fluid and homogeneous, there is no free energy difference for the protein as it rotates along its vertical axis. So you can have a spin angle here, and if you run a simulation long enough, you will see that the protein both diffuses laterally and rotates around this axis. And it can also tilt away from the same axis. So we have a spin angle phi and a tilt angle theta. And the tilt angle is actually more physically meaningful because as you change the tilt angle, the way that the protein will interact with the membrane will change as well. Both variables here, along as many others, of course, are variables that are provided as restraints, as collective variables that you can bias in Colvars. And I will just show here one full example of how you would write the Colvars configuration file or Colvars file or Colvars script, whichever way you want to call it. And this is the text file that you add to the NAMD configuration file, which is also a text file. And altogether, the two of them will direct what the simulation is supposed to do. NumD will specify what the physical forces will be from the force field, and Colvars will read the contents of this file to decide which variables to compute and which ones to restrain or to bias. So it's a text file that you can most of the time write yourself, but there's options to do so from a template, which is great. So first we start from defining the atom selections. In this particular case, we use an atom selection which is based on index files. Colvars also supports atom selections based on text, like NumD text, but we would like to use the index file because this way we can define a selection in VMT using the very nice, sophisticated selection language that it has, write it into an index file, and then use the same selection in NumD or the atom selections. We have some of them, but not all the ones that NumD has. So we define the groups that define that essentially one main group is the backbone of this protein. And we can define a collective variable with this block here. The block says this is a whole collective variable and doesn't say anything about the forces that will apply to them that will be defined in a separate section of the text. We'll give it a name. We'll decide which should be the resolution of any histogram or the magnitude of the restraints that we should apply. So the characteristic width, and this is a variable that has a range between -1 and 1. So we've been it running fine with a small width. And this tilt variable is the cosine of the tilt angle. And we define it based on the atoms that compose the group of the backbone group. And we provide coordinate files for the initial orientation and the initial structure of this group of atoms. And this is done with the XYZ file. We still support PDB files in VMD and NumD, but we prefer XYZ files for two reasons. One is they're easy to prepare because it's a text file that you can also make with the text editor. And of course, you can also use VMD to prepare them. Two, with the reader that we use in Colvars, use the full precision of anything you give in the XYZ file. So you can make the simulation very precise that most of the time for this kind of applications, a PDB file will have enough precision for the purposes. But if you use full digital precision, you can actually help us troubleshoot any bugs that may occur. Hopefully not in this code because this has been pretty stable for a decade and a half. And we define what the axis of rotation should be against. So we should be tilt angle away from the z-axis 0, 0, 1. Then comes the spin angle, is very similar to the tilt. And this is now a periodic angle, which is in the -180 to 180 degrees range. Same otherwise syntax as before. Now, in this simulation, we would like to use we would like to allow the tilt angle to change or to fluctuate around the landscape that is defined by the protein. That's a physical movement. But we know that in a periodic member, which is homogeneous, any spin rotation is not really relevant. So for the sake of making our life easier when we analyze the trajectory, we would like to restrain it. So we add the harmonic restraint on the spin angle here, which is centered on 0, starts basically no rotation compared to the initial structure that we provided. And we provide a magnitude for the force constant, which is the KBT, the thermal energy unit, 0.6 kcal per mole. And this is in the unit of kcal per mole divided by this number squared. So whenever you have 0.6 kcal per mole, which is the thermal magnitude of fluctuations, the spin angle will, the spin angle will fluctuate with a standard deviation of 3 angstroms because it was defined here as the width for the spin angle variable. And we can look at this simulation as it progresses. First, we start with a simulation where we just calculate the variables, but do not put any restraints. This is what happens. This is a ghost-clear simulation, so it will fluctuate over a short period of time, relatively fast. But nowadays, we can run multiple microseconds and longer atomistic simulations, so you would see the same effect. And this is what happens instead of the tilt angle. So the spin angle diffuses freely around as a free range diffusion, whereas the tilt angle is confined around the zero, or the cosine of the tilt angle is confined around 1, and there is a certain magnitude associated to the strength of the forces between the protein and the magnet. Once we put a restraint on the spin angle, we can just completely stop from moving, but the tilt angle seems to still fluctuate as much as it did before. Can we verify this is true? Yes. We can take the histogram of the cosine of the tilt angle without restraints. This is the normal simulation as you would do in MD without any Colvars restraints. And the one with the restraint on the spin angle is essentially the same. This tells us that we can, in many cases, restrain 1 degree of freedom by putting a restraint on a collective variable, and other degrees of freedom are not affected. They will still diffuse or fluctuate according to their own landscape. I'm going to make a very brief mention of the fact that there is, like in every software, technical documentation, as well as examples and tutorials, and even something that is even better in tutorials, which is automated templates to prepare the input. But first, if you are using NAMD3, as normally most people would, this is the section that you have in the NAMD user's guide for Colvars. And because Colvars is a relatively large piece of software, still smaller than NAMD, but it had a very long section to it. So we moved this documentation to an external page, which you can call SALT. And you see here the link for this address is specific to NAMD3. So whenever in the future you want to know what features are there for Colvars in the version that is distributed with NAMD3, this is the web page. And from this web page, we have a brief overview at the beginning, but the very first section that isn't just a quick summary introduction is an example, which is an example to define the steered MD simulation by pulling 2 groups of atoms together. This is not the cannoning, but you can easily replace the 2 ends of the cannoning here, and you get the same configuration for the example that Chris was showing before. I'm going to now turn over to Jerome, who is going to talk to you about some of the things that I mentioned and other cool things that I haven't mentioned yet, but I know that he's going to present, and I look forward to it. And I'll talk to you just for a few minutes at the end of his presentation.
Jerome, you can just wait.
Hello, can you all hear me? How's my sound?
It's a Jerome.
Okay.
Can you just wait 1 second?
So I couldn't quite make out what you just said with all the echo, but I assume.
Can you hear us?
Yes.
Perfect. I'm just switching here to the way of presenting. Can you now share your screen, please?
Yes. This and there we are. Okay, so there we are. Okay. So hi everyone, and thank you to Giacomo for already presenting a number of concepts, and to Chris for presenting another number of concepts and applications before. So I just want to wait, let me hide this a bit. This is so where does this library stand within the ecosystem of software that people use? So what do we do with Colvars? Colvars is used for simulations, but also visualization and analysis, and it functions by interacting with other software that it's usually bundled with through dedicated interfaces. And the software includes NAMD, but also, as Giacomo mentioned, TinkerHP, GrowMax, LAMPS. That's for simulations, and for visualizations and analysis, it's interfaced with VMD. And now, what's the merit of being interfaced with all of these different simulation software? Well, one of the merits is that these different packages implement a number of different models, like different force fields or types of models, like machine learned force field polarizable models, atomistic coarse grain simulations. And this is just the main. Most of them can do a lot of stuff, but they are specialized more or less in different types of models. And because they have these different features, they're also used by different communities to model different types of systems. So a lot of these are targeted towards biomolecules, but LAMS is more targeted towards soft matter materials, even though you can do that with NAMD as well. So that way, Colvars can serve a very broad community. So what do people do in practice? And what you do if you want to run a simulation using Colvars? But usually you need to start by designing the variables. That is, somehow you need to come up with the relevant variables for your system, as Chris discussed a little bit. And then once you have designed them, so you know what you want them to be, you need to define them precisely. That is, write a Colvars input that's going to be a mathematically precise way of defining these. Then probably run a bias simulation with NAMD, and then analyze the trajectory. Okay. So how does this work? Well, I'm going to discuss first a basic input quickly and how you can prepare this with VMD without all the trial and error of writing the input file yourself. Then how you run the simulation with NAMD in practice. I'm going to go into the slightly more advanced topic of making the most of scripts. The scripting possibilities of NAMD and Colvars are extremely powerful, and VMD as well. And finally, I'll talk about visualization and troubleshooting using VMD. So let's go. Basic inputs. So here's an example, another example of Colvars input. So this one is for targeted MD. So it's a bit similar to the steered MD example that Giacomo was presenting. Now, what is targeted MD? Targeted MD is driving a molecular system towards a certain configuration using a bias, a time-dependent bias on an RMSD coordinate. So what we do is we have two blocks here. This blue block is defining a variable, and this green block is defining the bias that's applied to it, so the forces. So the variable is an RMSD coordinate. We name it RMSD. This is the RMSD function that will compute this coordinate, and we define it by a set of atoms that are defined using, flags in a PDB file. That's a very NAMD-ish convention, using PDB files to define sets of atoms, and it's convenient because you can define them within VMD, so you can have a visual way of picking your atoms. And then we need reference positions, and this is called beta because it's going to be a beta. We're going to try and transform an alpha helix into a beta hairpin, and then we take this coordinate and we apply to it a moving harmonic bias. So we define the Colvars that are going to be affected by this, and the centers. So we start by having a restraint at a value of 5.3 angstrom. That is the initial value. So that's the value in our starting point. So we're not going to shake up the system too much. So initially, the restraint will be centered on the current value so that we don't already apply strong forces. And then it's going to be geared towards zero. So the target RMSD will move towards zero so that the system will be driven towards the reference 5. When the RMSD is 0, we're exactly at the reference configuration. And then this is going to happen. So this target centers defines the moving restraint, and target num steps tells us how many simulation steps it will take to reach this value. So we'll take these 200,000 steps, and the force constant here is going to be 100 kcal per mole per angstrom square, because here I haven't defined the width parameter that Giacomo mentioned. So by default, it is 1. So here we go. I define this and I start an AMD simulation. I started from an alpha helix, but you can see it's really getting distorted by the moving bias. And in a very short time, so this is probably 200 picosecond. If my time step is a femtosecond, my alpha helix has turned into a beta hairpin magically. So this is really the complete way of defining a moving bias and a targeted empty simulation. All right, so now how do I prepare this in practice? You know, it takes a lot of work to get this written exactly the right way. So can I use VMD to make that easier? So now I have my Colvars workflow, and then I might change my mind about the variable. So sometimes, you know, analyzing the trajectory will give me ideas about better variables. So what happens is we have this plugin that Giacomo mentioned, which integrates the whole process of going from the trajectory analysis to the design and definition in a more efficient way. So this is called the Colvars dashboard, and I'm just going to now show you how it works. So now I'm just opening VMD, and I've loaded a trajectory that I ran previously, and that's a protein ligand unbinding trajectory. So you can see the ligand, and I've been applying a time-dependent bias that tends to pull the ligand away from the protein, because the ligand otherwise would stay for a very long time, right? So this is what's happening, and the ligand is coming out of the protein. So now, now I would like to say analyze this trajectory and find the relevant coordinates. So what do I do? First, I need to open this plugin. So I go to extensions, analysis, because it's for analysis. And here's the entry, Colvars dashboard. And this opens a menu that has a list of variables that's now empty and a bunch of action buttons. Now, what do I want to do? Well, maybe I don't have any idea at all what I want to be looking at, but I know I have a protein, and so there is a little menu item here. It can create for me the most common variables that people typically use. So here is protein and nucleic acid autocolvars. So if I click this, it will detect that there is a protein in there, and it defines variables that are classically used for this. So now, you know, I didn't see a configuration file for this, but if I double click on one of these, it opens a little editor, and that shows me the configuration that was written for me. So even with a little comment that explains what's going on here. So now I have all of these variables, and if I navigate the trajectory in VMD, the variables are updated here. The values are updated because they're computed in real time by the C++ library that's embedded in VMD. And now, so let's say, suppose these are not exactly the ones I want, because they're just, you know, about the protein, the RMSD or radius of gyration, and some measure of the protein's orientation. So I'm just going to say, these are not the ones I want. I hit reset, and off they go. And now I'm going to say, how do I measure the ligand going away from the protein? Well, you know, in VMD, you can measure distances between atoms. You can label them just by this tool using the mouse. So mouse, label, bonds. And then clicking on two atoms will label a bond, or just a distance between two atoms. Here, they're not bonded. So now I have this VMD distance between two atoms. And this is giving me an idea of the distance between the ligand and protein. So now I can just click on this second button in automatic Colvars. So use Colvars from VMD labels. And now this distance has become a collective variable. So if I double click here, I now have the input for a distance coordinate based on this VMD label. So this is cool. And now maybe I could plot a timeline of this. So all the plots and visualizations are in this segment of the menu. And this is what a timeline looks like. So if I animate, it shows me a time cursor that tells me where I am in a trajectory. And conversely, if I see some place in the trajectory that's interesting in this collective variable, I can click on this graph, and it will take me to the right part of the trajectory. So this is really useful if there is an interesting event that happens here in the Colvar space, and I want to see what this event corresponds to in the space of atomic coordinates. Now, suppose this distance, I just picked a random atom from the ligand and a random atom from the protein, so that's not really a very good coordinate, right? So let me fix that. I'm going to now fine-tune this coordinate by double-clicking it. And now first I can rename it. I don't want this very long name. I'm just going to call it D. And then it's a distance between two groups of atoms. So I'm going to change these groups to be maybe, well, all the heavy atoms of the ligand. And what's convenient is that I have them visualized here in a representation. So what I can do is I can select this and ask VMD to replace it with the atoms from a representation. These are the selection text in my representation. So this is the ligand, res name lig and no H. So now I can remove these extra comments, they're not very interesting. It has replaced, it has detected that these atoms are a certain range of atom numbers here. And then the other group is one atom from the protein. I don't want one atom from the protein. Maybe let's have the distance from, how about the alpha carbons of the protein within a certain distance from the ligand. Can we do that? Well, yes, we can do that because we have VMD atom selections here. So let's say alpha and within maybe, 15 angstroms of res name lig. I hit enter, and now I have this new selection with a bunch of atom numbers. Let's apply it. Okay, so the value has changed. And if I click on the timeline, you can maybe see that it's a bit smoother and it really just goes up in a more consistent way. So if I want to see what these atoms really are that I've just selected, there's this button here in the visualization. I can just display the atoms that are involved. So show atoms, and this shows me color-coded by atom group. There's a red group of atoms, these are ligands, and a black group of atoms, or gray, that is a protein. So this is what my coordinate is. Now imagine I want to, say, apply a restraint to this coordinate. I can just right-click and click here, add harmonic bias. And this opens an editor for the input for harmonic bias. And maybe the center should be whatever, maybe 10 angstroms. I'm applying this. And if I go to the biases tab, I now have a harmonic bias defined. So once I have this, I have a coordinate of bias. That's all I need for a biased simulation, right? So I could do save and save it to a Colvars configuration file that I can then use in MD. So I really haven't had to write anything from scratch. And if I'm in doubt about anything while editing the configuration, so I can use any of these different templates for Colvars or for the components, the basis functions here, like a distance, and other more specialized templates. So I have these helpers for the atom selections. And finally, in doubt, there are links here to the documentation for these different essential notions. Okay, so this was editing the configuration file, and now this file can be directly fed to NAMD to run a bias simulation. So how does that work? Let's see. Okay, how do you simulate this with NAMD? Well, if I have a regular NAMD configuration file without Colvars, I just have to add these parameters, the first two, activate Colvars, and then give it the configuration that I just made with VMD. And then if I'm restarting from another NAMD simulation, I need to add this Colvars input flag and give it the Colvars.state, which is really the kind of checkpoint that remembers the state of a Colvars simulation. Then start NAMD, maybe with using several cores of the CPU, and then the NAMD input that will contain this, and keep a log file. That's always useful to understand what's been happening after the fact. Now, what's in this log file? Well, this log file has a lot of information. I know it's a bit intimidating, but I really recommend that you try and skim through it at least, and understand what it's about, and see if there are and get get people like NAMD experts to advise you if you don't know what the log file is about. So here, there's one section in the log file that is all about Colvars, and when it starts up, it says this message and gives you the version of the library that you're using, which is very good if you're in doubt about what's supported or not supported. You can check the documentation for this version. If you see something that looks like a bug, you can report it and say, I'm using this version of the library. And then we know exactly what you're talking about. And maybe we'll tell you, oh, that's a known bug and it was fixed in the next version. So you just have to update. Then the next little section reminds you of the reference paper for Colvars in general. And then it reminds you that later on in the output, after everything is initialized, it prints a list of papers that correspond to the features that you're using for this particular simulation. So that means if you publish this simulation, you get directly the bibliography that you should cite for the simulation. And then there's a little section that tells you about the features that are enabled in this particular binary that you're using. And so one of them tells you about the parallelism. So Colvars can run in parallel on different CPU cores, and then it tells you how many threads it can run on. And then it tells you about whether you can use custom functions and if you can run TCL scripts. Okay, so I'll go back to that. So what's happening under the hood once you run this is in NAMD? Well, NAMD is maintaining atom coordinates. It's computing energy using force fields and forces. And these atom forces are used by the integrator to update coordinates. And say, if you're running NAMD 3 in its GPU resident mode, all of this happens on the GPU. The atom coordinates are stored in the GPU's memory, and the computation is done on the GPU. And then on its side, Colvars is maintaining a list of collective variables, which are possibly combinations of these basis functions that we call components, and then different biases. And based on that, it's computing Colvar forces that are applied not on atoms, but on the variables themselves. And in the middle, there is a proxy, really a communication system that gives, passes atom coordinates to on one side and passes back atom forces on the other side. So one thing I forgot to say is that Colvars lives so far on the CPU only. So the data, like these coordinates, have to be copied to the CPU, the main memory, and the computation is done on the CPU. One thing is then that can have an impact on performance. So let's look at performance issues. There's two kinds of performance issues that could happen. One is computational issues, meaning, if you have something really that takes a long time to compute, then the rest of the work, if NAMD is very parallelized, so all the other tasks are going to wait for that one task to finish. And the second type of bottleneck is communication, which means if different parts of the calculation have to communicate, of course, you can wait for the messages to arrive. So that's another way that can limit your performance. So Colvars, as I said, always run on the CPU, but it does take advantage of multi-core CPUs if you have this SNP option enabled, which is default, and you can double check it by looking at your log file. NAMD 3 can run GPU resident, so as I said, it requires this data transfers. And the other consequence of NAMD running GPU resident is that it's typically faster, sometimes much faster. So the faster the simulation itself is running, and the more probable it gets that the calculation on the Colvars side becomes a bottleneck. Although it rarely is a very large bottleneck, because the calculation that Colvars typically does is much cheaper than all the computation of forces that NAMD has to do. So what do you do if you're not sure or if you don't get performance that you'd like? Well, so last thing is when does Colvars become a computational bottleneck? Well, if the computing the Colvars themselves is expensive, and the most expensive one is this coordination number, because it has to compute essentially distances between all pairs of atoms in a set of atoms. So that can be improved with a pair list system that you can find documented in the user guide for that. And then what makes the communication a problem? Well, anything that has a great many atoms will make communication slower. So the solutions to that is, first, tune the performance of NAMD itself. So you could try not enabling Colvars and doing the performance tuning that can be done in doubt. There is a little section on the NAMD wiki about performance tuning. I'm not sure it's entirely up to date, but in doubt, if you really don't see the performance you expect, you should ask your local NAMD experts or the mailing list if there is a way to improve the throughput of your NAMD simulation. And then for Colvars, don't use more atoms than necessary. For example, don't restrain a protein by putting restraints on every single atom of the protein. It's usually not necessary. It won't make a difference. If you have several variables, several expensive ones, don't forget to enable SMP and to reserve several CPU cores on NAMD, which is something you might forget because if you're running GPU resident, you think, well, I don't need the CPU really, but Colvars will need or is able to use several CPU cores. And then if you have Colvars that are really slow, you can also enable this time step factor option, which essentially makes the calculation of Colvars happen only once in a while, so once every few time steps. And that, when I say slow Colvars, that means two things. So I need to be more precise here. I mean variables that, here I don't mean variables that take a long time to compute, but that's only, of course, that's when it's going to be useful, but also mean variables that don't change too fast in time. So, which is a bit like the long-range forces that you can optimize in NAMD by computing them only every few time steps. So this is different ways to get better performance out of Colvars. And now, as I said, a very special feature of NAMD and VMD and Colvars is the way they're very scriptable. So the flexibility happens not just through scripts. So you can expand the range of variables that you can create by combining the basis functions that are implemented. You can make polynomial combinations, so sums of different powers of the variables. And then you can also use your own symbolic expression using the Lepton library. So it's basically writing standard math like, cosine of x plus sine of y, and that will automatically compute the variable. That at least is possible in NAMD. It's not available in standard builds of VMD so far, although we are working on that. And by working on that, I mean working on trying to convince Urbana people to include this into VMD because it's working in our hands. And then you can also write TCL scripts, and I'm sure you've been hearing about TCL already, and you're going to hear more about it. So TCL scripts let you define new variables, but also new biasing algorithms. And finally, the NAMD config file itself is a TCL script, so you can script NAMD's behavior together with Colvars. I try to give you examples. So one example, this is an example of how you can script a new biasing algorithm using a TCL script without writing C++, without recompiling anything. So it's this, the example I'm taking, this adiabatic bias MD, so ABMD, which is a way to force a coordinate to move forward, but without applying this constant velocity bias like steered MD or targeted MD. So what happens is there is a harmonic restraint that is just moving behind the coordinate, and that lets it move forward, but prevents it from moving back. So let's see what happens on this little toy example. So my coordinate is here at the red point, and the green thing is the bias, and the bias is just moving forward, and it moves forward. And so that helped it, it selected the fluctuations that made it move uphill. And then, of course, once it reaches the top of the barrier, it goes downhill. And I've crossed this barrier using this method. So now how do I implement this? Well, one way to implement it is really simple. You can add this new method into Colvars without writing any C++ code. So the quick implementation is the following. It's a little Colvars TCL script, and I just defining this function, which is called the procedure in TCL, where I say, well, I need the value of the coordinate. So I'm going to call z a variable that contains. So here I'm calling the Colvars scripting interface and asking for the value of Colvars z. Then if that is higher than the previous highest point, then we need to move the previous highest point up. So, and it has to be lower than the target, because there's also a target where I stop moving. So if it's also lower than target, then the new maximum is the current value. And if it's not, that means behind. And if it's behind, it's in the harmonic potential. So I just add a force to this variable using the Colvars interface. And the force is a harmonic force, so it's just a linear function of the distance to the reference point. So, and then, well, that's it. So this function here in itself implements a whole new time-dependent, adaptive biasing method. So of course, some of them, the others are more complicated, but still, this is, I think, an example of how powerful it can be to use this scripting interface. And so in the Colvars config, I just need to add this line, scripted Colvars forces, Colvars forces on. And once I enable this, Colvars will automatically execute this function at every time step to see if it needs to add new forces. And of course, define the variable itself. Now, slightly more, an even broader example that can show you how you can really change the behavior of your simulation, and the sky is the limit, is an example where I want to script the behavior of NAMD by calling Colvars. So imagine this is in a NAMD config file, and I want to do something in a loop. I want my simulation to proceed until I hit some condition, maybe until my variable reaches a certain value. So in a while loop, I'm just going to, detect the value or compute the value of the collective variable. And then I can change the Colvars configuration. For example, I could create or delete or modify the collective variable. If the collective variable is not the right one anymore, I can detect that and change its definition on the fly in the simulation. And then if, according to a certain criterion that I'm computing myself, I decide that the simulation is over, then I can set a terminate flag to true, and then I'm done. And otherwise, I just run using the NAMD run command. I run another set of simulation steps. So this is really a fully adaptive simulation that is going to react to what happens to the variable. And this is just coded using the TCL scripting features of NAMD and Colvars. So now I see that I'm out of time, so I'm going to be very quick with this final step, which is how do I use can I use VMD to analyze and troubleshoot my Colvars simulation? So let me go back to my VMD session here. So now imagine I've been running a bias simulation and I want to see what happened. Well, let's see. One thing that's really useful is imagine my simulation has crashed. So if it has crashed, and I think it's because of Colvars, maybe it's because I've been applying large forces. So then in this biases tab, I can, so if I load, I reset and I'm just going to load the input that I've been using for the simulation. So I load this file and all of my variables are here and the biases are here. So the simulation had a bias on this. And what I can do is I get statistics here. The energy here is the energy of the Colvars, and it tells me what the highest value of the force, what the highest atomic force is, and which atom it was applied to. So if something, if my simulation had been in trouble here, I could just check what happened to this particular atom. Then if this is not clear enough, I can just click here, show bias forces, and these arrows tell me exactly what forces were applied where along the simulation. So here, this is the Colvars that's included in VMD, recomputing everything based on the coordinates, based on the trajectory. So now what happens if I think maybe there's something wrong with the way the coordinates, the Colvars are being computed here, or there's something wrong in the simulation? Well, then I can just maybe forget about these, and I'm going to load the variables from the trajectory file. So here, this is something that was written by my simulation, and these are the variables as they were computed, not in VMD, but in NAMD. If I open this file, now I have all of these, which are, which have a prefix of traj, because it means they are recreated from the trajectory. And now I could compare the values of these with the values that I see in VMD. So that's one way to make sure that I'm looking at the values as they were computed in VMD. I mean, in NAMD. So one thing that I recommend you to be particularly careful with is PBC, because one classic problem is if you run a periodic simulation and you define atom groups, especially when you restart a simulation, the atom group could be broken in two pieces on either side of the periodic box. And if you do that and you compute, say, the center of the atom group, then the center of these two parts will be in the middle, so not really in a sensible location. So usually visualizing a trajectory in VMD and double checking that the values computed by VMD and NAMD are the same is a very good way to detect that kind of phenomenon. And with that, I'm going to yield the floor again to Giacomo.
So, gentlemen, I have a question. Can you hear me?
No, that one, it's another one.
Okay. Jerome, Emad has a question for you.
Oh, yeah,
Should I come down here?
they should be able to hear us. It's from here.
Hi, Jerome. Can you hear me? Apparently not.
It's Giacomo, can you hear us?
Oh, I'm sorry. That was me. I muted myself.
Okay.
I can hear
Now
you.
you can hear us, right?
Yeah.
Okay, so when you do some transformation to your coordinate, do your force vectors also move with the coordinate? Like, for example, when you superimpose to remove the translation and rotation of the protein, the force vectors also recognize this and move with the atom coordinates, right?
Yes, I can show you an example. So let's say I'm showing the forces here. So now, let's see. I can even, so using VMD, I can do something like move the molecule even with my mouse. So here I say, like, what happens if the ligand is here and rotated instead of being there? And then I need to press F5 to refresh or click refresh, and it's just recomputing everything. So I can even look at what happens to coordinates that were not in the simulation, but coordinates that I've been modifying. Oops, here I'm touching protein. So yeah, everything is updated every time I press F5 or refresh here.
I see. Very, very, very nice. Very nice. Again, I congratulate you guys for this, and I highly recommend everybody to use this very powerful, actually, interface to work with Colvars and take advantage of this powerful technology, actually. Thank you. Thank you.
Thank you.
So, I don't know, Giacomo, are you going to continue with something, or are there questions you want to answer?
I'm going to move very quickly through our last
Go
couple
ahead.
of slides because we're going out of time.
Okay.
Thank you, Jerome.
No. Okay. I was just reprising the example from before to show that once you have protein, remember, has different has a certain variance for the tilt, and this variance can lead to a PMF, which you can get by taking the logarithm of that histogram, and that PMF you can reconstruct with any of the NXL sampling methods that we have. This is an example from metadynamics, and you can also, just using the VMD and the dashboard and maybe some other analysis tools that you can apply onto the system without looking specifically at the protein, but you can rationalize what this PMF is about. And in this case, it shows you that the PMF is given by the amount of distortion that the protein induces to the membrane as it rotates. And if you want to specifically restrain the membrane and to measure the free energy of that distortion, there's a method for that. I mentioned it because of the value, but also primarily because this is one of the very few corrective variable types which is available specifically for NMD. This is a corrective variable that you can apply to, for example, reconstruct a potential main force as a function of a membrane that is getting increasingly bad. And the algorithm used for this PMF here was umbrella sampling. This is something that Chris has mentioned at length. And yeah, another thing that I could mention, but go very quickly because Jerome already introduced concepts. Colvars is a CPU code, so the simulation will be slower, but there's some cases where you can eliminate that slowdown because the centers of mass are computed in parallel by NMD. So any function, for example, distance between two groups, if you're on CPU-based NMD or with GPU offload, not GPU resident, there is actually very little to none overhead from Colvars. And multiple functions can be computed in parallel. The volumetric maps are also one other example, along with the centers of mass. They're computed entirely in parallel with very little overhead. Hopefully, there will be more in the future. And Jerome already mentioned the time step factor, this multiple time stepping scheme that you can use to compute variables only every few steps. How does that work with GPU resident NMD, which is something that you're using at length in this workshop? Again, I'm going briefly, but only showing basically the data on a benchmark for one membrane protein simulation by using multiple GPUs, and this is done for standard NMD. And Colvars is, of course, computed on CPU. A recent feature that was added by people in the NMD team, primarily Eric, with some technical help from David and other people that contribute various pieces of code. And also here I'm showing an example with the Colvars that is being computed using another NMD function, which was recently improved by Hao Chuan, who has contributed a lot of code to Colvars and is also a member of the NMD team. So this is what you get. This is not to dissuade you from trying these calculations, but be aware of the fact that when you're using lots of atoms in a corrective variable, you pay a price for it. In this case, there's a price done by the computation that Colvars needs to do. And this is a single MSD function, so our parallelism on threads is very limited so far, so it doesn't break it up over multiple threads. So he has to wait to compute the MSD of those atoms on the CPU. And then also, there's a lot of overhead done by communicating the atoms from the GPU to the CPU part of NMD to the CPU part of Colvars and back again for the forces. Unfortunately, you cannot benefit as much from multiple time stepping because multiple time stepping so far reduces the amount of computation that Colvars does. And in many cases, as Jerome said, the amount of computation is not a lot. A lot of the slowdown that you may get is from communication between multiple nodes when you're running parallel, communication between CPU and GPU when you run on GPU resident. So things can be actually much improved if you use a variable with specifically just as few atoms as you need. If you want to restrain the overall structure of the protein in a loose way, in a relatively coarse way, but getting all the fundamental features, you can just use the C alphas, and it gets a lot better. And here, in particular, for this configuration, for this system, which is 300,000 atoms, but less than 3,000 atoms, including the MSD, you get like a less than 20% slowdown. And again, the computation is relatively cheap. The communication is what matters here. And so you can try multiple time stepping. In this case, it doesn't work, but it will help you if you're running NMD and Colvars primarily on CPUs because their computation and communication are both under control of the CPU. But this is just a word of caution to, especially when you use NMD GPU resident, to be mindful of the fact that some configurations will be very slow other ones will be actually acceptable. And thank you to everyone who has been listening to us, to the people who worked with us to develop Colvars in the past 16, 17 years, and to our colleagues with whom we interacted and gave us input in terms of good ideas and especially feedback. And to you guys, we hope you try this code out. You definitely will with the tutorials and later on as you progress with your projects. Thank you.